Hello, everyone. This is the CFD short course at CHT 21, and we are on lecture 6, turbulence modeling. Usually, we spend a whole quarter at least teaching turbulence. Certainly not less than 8 lectures are needed. But anyway, just to give you an idea, here is a brief summary. So here are the goals that I've set for this talk. I want to give you a brief overview of turbulence models and a very concise introduction to physics of turbulent flow, which is very interesting and very complex. And to give you some insights into the use of various turbulence models for practical problems. And finally, what their limitations are. So as far as the physics of turbulent flows is concerned, there are a wide range of length, velocity, and time scales. And they are aspects of energy transfer from the large energy containing eddies to the small dissipation eddies. Then one thing interesting happens, which is the behavior near the wall of turbulence is very different than that away from the walls. There have been many models devised over the last, since 1905, I believe. So zero equation model of Prandtl was perhaps first that revolutionized turbulent practice of turbulent flows. And that still is a good model in many situations. When boundary layers dominate, jets, wakes, all that, it's a very good model. Then there are one equation models that were devised over the time. The K epsilon K model that I used for my thesis is a one equation model combining with Prandtl's mixing length. Then there is the eddy viscosity model, which are becoming quite popular in some segments of applications. And there was Bradshaw's shear stress model, which also had very good performance for certain kind of flows. But the most popular today are perhaps the two equation models. K epsilon leads the pack, more or less. There are various versions of it. And then there is the K omega, which was popularized, first discovered first put together by Safman on a firm footing. Actually, there's an interesting history here. K epsilon actually was first used in a published paper by Harlow and his group. And then Brian Spalding and Brian Laundrer put that on a standard footing and became a very popular model. K omega, we also played at Imperial College, but we discarded it because of some nonlinearities that occurred in certain terms. So Safman put that on a firm footing, and his student Wilcox took it much further. Mantra and a number of other people have played with K omega epsilon models, which are called the blended models, where epsilon is used where it's useful and omega where it is useful. Then there are, of course, the K tau shear stress type of models. There are KL models, sorry, not KI. And then there are algebraic and Reynolds stress models, which deal with anisotropy of turbulence a little better. And then, of course, now there's the LES, DNS, and different variations. Now, the fact is that whenever you have too many truths, and that's what a model means, it means no one yet knows the truth. Okay? Model is a polite name for our ignorance. Imagine for a minute, I write a proposal to you and you are in the chair of the guy who gives me the money and you say, hey, I want to improve my ignorance. Can you give me some funding so I can put a student to work on it? Well, you never look at that proposal, right? But if I say, hey, I want to get a new turbulence model, there you go. Okay. So let's look at the nature of turbulent flow. Turbulent flow is irregular, highly stochastic, and random. But it's not random in the pure sense of randomness. It statistically has distinct averages. There are eddies of certain scales, and they talk to each other, okay? So it's not completely random in that sense, okay? It's stochastic, but not random. It's unsteady, always. There is no such thing as steady turbulence, okay? You can average it for your purposes, but fluid doesn't know something called steady state turbulence. It's a 3D phenomenon. Again, there's no such thing as 2D turbulence. Okay, a fluid, if you give it a true 2D flow, there'll be no turbulence. I guarantee you that. Okay, so vortex stretching can only occur in 3D phenomena. Okay, it's highly vertical, it's eddies, swirling flows, rotating motions, and all those things. What all those things do, what turbulence does, is enhanced mixing compared to laminar flow, as if the viscosity of the flow was much larger, much larger, could be orders of magnitude larger than the laminar viscosity. So it's very useful in those situations where we want to enhance mixing. Okay. It is a continuum phenomena with very wide range of length and time scales. It's continuum because even the smallest scale, the Kolmogorov scale, is above the molecular scales, well above. Okay, so it still stays a continuum, but it has all the structure within that. Okay, and it's distinguished by large Reynolds number. At small Reynolds number, there is no turbulence in most situations. So let's look at what happens. Eddies are highly vertical swirling flows. They're convected with the flow. Okay, so we have this turbulent eddy moving about and fluctuating and all that. It's being carried down the flow just like an entity. Okay, of course, it's stretched and all that changes. Eventually it will change, but it's being stretched now. Richardson made a very nice ditty for that, which says big wholes have little wholes that feed on their velocity, and little wholes have lesser wholes, and so on to viscosity. So that is the truth. The big wholes get the energy and the little wholes dissipate it. Big eddies don't stay necessarily big. Okay, they stretch, they break, and they could change eddy sizing. Okay, but large eddies are generated by the instability in the turbulence flow first, and then they are then broken down into smaller ones. So large eddies are the one that extract the energy from the mean flow, so to speak, or from the rest of the flow. Okay, so that's the production of turbulence energy. Okay, and that only occurs when there is a velocity gradient in the flow, right? It's needed to create energy. Okay, the smallest eddies then dissipate this energy through a cycle, through a cascade, and the cascade looks like that. The large eddies take the energies, and they are at the macro scale, the length scale, LM, which is the scale of the eddies, right? Now, these eddies then go through an energy cascade and eventually come to the smallest eddies at this scale, okay? So the scale is increasing this way and energy is flowing this way. So how it is distributed? Let's define a few quantities. There is a wave number kappa that is proportional to the reciprocal of the eddy size, okay? So smaller the eddy, higher the wave number, okay? That's usually what happens as length increases, the wave number decreases, okay? K is the turbulent kinetic energy. It's the kinetic energy which is only the turbulent component, the fluctuating component of velocity, not the mean velocity, okay? You have to subtract the mean velocity from the total velocity to get the turbulent energy. Epsilon is the rate of dissipation of this energy. This is what viscosity is doing. It's dissipating that energy, and epsilon is that. So Kolmogorov developed a hypothesis after looking at experimental data, which I'll show you in a minute. And he said that the energy cascade over the kappa, over the wavelengths, is given by this quantity. It's proportional to minus 5/3 power of the wave number and proportional to this 2/3 power of the dissipation, okay? So this is the minus 5/3 law there, where epsilon is dissipation of turbulence energy. This is what the energy spectrum actually looks like, okay? This is, of course, for one flow situation. Others would have a different one, okay? But this is for certain class of turbulence, this is what happens, okay? So this is typical. There's a lot of production in certain states, is the production region, and then there is the inertial subrange, and then there's the dissipation region, okay? So in this inertial subrange, you'll find that if you plot log K by log of energy spectrum versus the wave number, you'll get this minus 5/3 slope. Okay, so that's where this number comes from. And this is very useful when evaluating results from the LES. You should get these far away from the walls. Now, the important quantities are the dissipation epsilon, the kinematic viscosity nu that dissipates the energy, and by dimensional scale, we can take a length scale, which is the Kolmogorov length scale, okay, the eta, and then the velocity scale u eta, and the time scale tau, okay. So dissipation rate has this units, length over time cubed, okay, right? We'll see its implications from dimensional analysis. And kinematic viscosity, of course, is length square over time, right? So if we use dimensional analysis, we can define a Kolmogorov length, which is this quantity, a time scale, which is this quantity, and a velocity scale, which is this quantity, right? Okay. So if we do that, we'll find that the Reynolds number from these at the Kolmogorov scale is unity. That's what's implied by all this. So smallest eddies at the Kolmogorov scale have this Reynolds number, and these are the ones that dissipate through viscous action. Now, when we come to large scale, there is a length that defines the large scale eddies. Of course, different eddies would have different scales. So different L scales, the number of L scales, and Rota did a lot of work on this. But let's just talk of the average length scale that distinguishes the large eddies, okay, which will be, of course, a different sizes, but we're talking average, okay. If we do a dimensional analysis, we'll find that this is how the basic relation is. The dissipation is related to 2/3 power of the kinetic energy divided by the length scale. That's what dissipation is, okay. So if we define a turbulent number now, a Reynolds turbulent number, which is the Reynolds number for turbulence, okay, based upon these large scales or macro scales, then we get Lm root of kappa, which is velocity, and then viscosity. So here are the length scales, relations between the length, time, and velocity scales. Length scales are proportional to 3/4 power Reynolds number, velocity to the quarter power, and time to the half power, okay. This information is critical when estimating the mesh and time step requirements. This quantity, the 3/4 here, is very crucial. That's why we cannot go to high Reynolds number, because the step in the length scale involved to resolve these would be too big. So near wall turbulence is characterized in wall units. Near wall turbulence differs from the turbulence away from the wall, because turbulence away from the wall is largely isotropic. There is no specific direction, so everything looks about the same, okay? But when you come near a wall, there is a wall. Nothing can cross the wall. So the eddies that come close to the wall, they flatten out, okay? So what happens is that they stretch in one direction, and the fluctuations in one direction are much more than the fluctuations in the other directions. Also, there's a no slip condition at the wall. That means the wall must have the same velocity as the fluid, or fluid must have the same velocity as the wall. And if wall is moving, fluid is moving the same speed. If wall is stationary, fluid is stationary. So zones close to the wall are dominated by viscous action. That's where the gradients are larger, and that's where the action happens. And this is called the laminar sublayer or the viscous sublayer. So since the velocity at the wall is 0, we can define a suitable scale by defining shear stress. Now, for typical boundary layers, shear stress across the layer is constant. Okay, it's an important fact that is observed in real life. So what we do is we define a u tau, which is the velocity based upon the shear stress. Okay, so this is, if you take the shear stress, divide by rho, and take square root, you get a velocity, right? This velocity is called the friction velocity. Now we can use this friction velocity to non-dimensionalize our distance. So the non-dimensional distance is basically y plus, and u tau comes here, the velocity times this over viscosity, this is y plus. Of course, we also in many situations, you'll see a u plus. U plus is nothing but u over u tau. Okay, that's a non-dimensional. Okay, y is the distance perpendicular to the wall. So if now we look at the velocity gradient of the wall, you'll find that because we have the requirement that there should be a certain shear stress, you'll find that what that means is u tau contains the shear stress, right? So dy would have to be this function. Okay, it have to be u tau, the shear stress velocity, divided by the distance, and some non-dimensional function on y plus. Okay, so experimental data indicates that for large values, this becomes 1 over kappa. So this function becomes constant when y plus gets large. Okay, so we define this dimensionless velocity, and we know this, that it becomes 1 over kappa. If we put it in this equation, what do we get? We get u plus is equal to 1 over kappa log n y plus a constant. This is the famous law of the wall, log law of the wall. Okay, and this is what the u plus, or shear stress, distance, not velocity normalized by shear stress, would look like versus y plus. This is the famous plot, u plus y plus, and this is what happens. This is actually linear in physics. This is a log scale, so it becomes like that. But this is actually linear, and this is actually the one which is highly curved. So this becomes the linear. This velocity changes linearly very close to wall, because basically it's only the laminar viscosity, molecular viscosity, that is affecting it. Okay. Now in this region, there is turbulent viscosity becomes significant or becomes increasing, and here it dominates. Okay. So this is the log layer, and then this could be eventually the defect layer, which could be close to the free stream. Okay. So this is what happens, and this is a log law distribution, the wall. Now let's come to the need for the turbulence. Well, why do we need turbulence models? We have now your Stokes equations. We agree that they solve the equation, so why not just solve them? Okay. Well, here is the conundrum or the problem. The ratio between the largest and the smallest eddies, based upon the Reynolds number, is Reynolds to the 3/4, right? In 3D space, this means that the Reynolds number dependency in 3 dimensions is based upon Reynolds to 9/4. Okay. Also, we know that to resolve up to the Kolmogorov scale, will need very time steps of that order with the characteristic time steps. Okay. So if we want to do, we need to resolve everything in DNS all the way to the Kolmogorov scale, right? Well, that just is not possible because it's prohibitively expensive and time consuming. And for most practical problems, except some, there are some exceptions, it's not feasible today. Of course, it can be, may become so, especially with quantum computers. We don't know that. Okay. But till we do that, we are stuck with the turbulence models. So there is some further information by Wilcox and by Pope. So these are good books to take a look at. Now, how do we model them? What we do is we can't deal with the whole complexity. So we say instantaneous quantities are decomposed into some of the mean and the fluctuating component, right? So anything like velocity is split into velocity is equal to instantaneous velocity equal to a mean value and a phi value. Okay. So over bar indicates mean and prime indicates bar. So various kind of averages are possible here, right? We could do it average over time. We could do spatial averaging. We could do average over space, over eddies, for example. Okay. We could do ensemble averaging. We could take 50 realization at the same point and say this is the average value. All these are there. Okay. So all these are defined in more detail by Pope and Wilcox. Okay. By the way, Wilcox is generally easier to understand. Pope is more thorough, but also there's a lot of math in there. Okay. So now let's look at the Reynolds average. Okay. The Rand's equation, the so-called, we get them by saying, here it is. If we put these quantities, if we split, we assume rho is constant here, otherwise it just makes more complex when rho is changing. But let's assume that u has a mean value of velocity. So this is what the continuity is. This is what the one is. So the continuity doesn't change much. Okay, there is nothing, there is no instantaneous value in the continuity. Okay, it's average instantaneous, doesn't change. But when you look at this equation, this is the regular Navier-Stokes equations, plus a term arises from this convective term, okay, and term which is u I prime, uj prime. Okay, this is the turbulent shear stresses. Okay, and this is what they look like. So these are the Reynolds stresses, they are called. Okay, they are arise simply because we are doing an averaging, and when we're doing certain things are averaged, and they make themselves manifest through this quantity. Now, there was a Bosnesque hypothesis that says that the Reynolds stresses are related to the velocity gradient via an isotropic eddy viscosity, just like molecular viscosity. Okay, he said, well, turbulence is really not any different than Brownian motion at the molecular level. Okay, if so, then we say, well, we just replace mu by mu t, and that's the turbulent viscosity. Okay, so that's what we basically did. Okay, so this is the basis for many common models, such as mixed line model, K epsilon, K omega, etc., and the mixed or blended models. So let's look at the linear eddy viscosity models. Okay, now the linear eddy viscosity models basically say that the shear stress is simply a viscosity times this. Well, no different than the laminar situation, or where molecular viscosity dominates, that will be the viscosity there, right? So we could modify that, which we do sometimes. We could say it's nu plus mu t, right? It depends on which model we are using. Okay, so here is it's one, we define a U mix, some kind of an average U for the mixture, and we define an average length scale, right? If we do that, then this component, the viscosity, is actually U mix and V mix, right? Okay, and you multiply by that. So viscosity is basically a function of these two quantities. You'll see it has the correct units of L squared by T, right? Okay, so the mixing velocity scale we can say that what is the mixing velocity, or what is the turbulent, if you want to say that component, the turbulent component of that velocity, which is at the shear stress level. Okay, so what matters is how the gradient changes, right? So why don't we say that's proportional to length time the gradient, local gradient. Okay, this is very convenient, and this is what led to the Prandtl's mixing line model, where he says U prime V prime is nothing more than L squared du dy and multiplied by du dy. This quantity is always positive because viscosity should by nature be positive. Okay, negative velocity is not possible. It will not satisfy the second law of thermodynamics. So this is very simple but very important thing that Prandtl did. Now he said length scale is basically varies linearly away from the wall. He made this L proportional to the wall, and then away from the wall he made it constant by looking at the data. Okay, well, Van Driest came along and he said, well, let's assume that there is a variation, and I'm going to use an exponential variation, which makes it a little better to match with the practical experimental data. So that's how we get this one, but it's still the same kappa is there. So this was L is equal to kappa times the distance. This is L is kappa times the distance times a function, which is a constant, one more constant he introduced. Okay, so the two equation model, the length and time scales are contained by solving a transport equation. Okay, we are actually solving for length and a time scale, which is same as a frequency. So actually, a frequency model would be more useful. But but let's say that we can use any second variable, okay, which is convenient to us. So this is what happens. Okay, here you see in this model we put mu plus mu t by sigma k, but this is a Prandtl number of turbulence, right? This is again realization because of the Bosnesque approximation, and we know how the flow behaves for different, the viscosity doesn't have the same effect as on turbulence energy, as on heat, as on epsilon and all that. So there is a turbulent Prandtl number for each of those, okay? So if we do that, this is what the equation is. There is a production term, which is related to the gradients in the flow. And then there are other terms that contain, number of constant, the dissipation term. These are added depending upon the model. This PB and DC are specific to different models, they were not in the original models, okay, but they usually today they are used, okay. So the epsilon equation is similarly today added one more constant based upon this production, okay, and then we have these two standard components of it, okay, and the viscosity now can be determined simply from another constant, C mu, K square over epsilon, that's viscosity. So this class of models solve the K omega model, solve for the dissipation directly, solve for the, you might call a scale, which is the time scale, which is vorticity or represents the frequency, okay? So this basically is related to the epsilon that we solved for. If you put epsilon equal to this, you will get this equation from that one. The constant and some other realizations are different because there's a lot of matching that goes on in finding the right constant. This is what a standard K omega model that Safman derived would be, and this is what happened. Okay, so here basically again the same linear viscosity used, and it's K over omega here, right? So this model is better near the walls because it displays it's easier to specify the boundary condition with this, which are very difficult with K omega. So that was the advantage of the K epsilon. So the advantage of the omega model, basically you are to deal with near walls. There is a better theoretical basis to specify what omega will be than what epsilon will be. However, this is very sensitive to free stream conditions, which can be very undesirable. So you have to be careful. So this is what led to the development of the blended models, okay? Because the standard omega model would have problems near the free stream. It would be very sensitive to free stream, and the whole things would change if you make a small change, okay? So that's what the blended models are. They use omega near the wall and epsilon away from the wall. So let's look at this wall, what caused this. So the wall impacts turbulence in two ways, okay? Turbulent fluctuation normal to the wall get damped. You know, they can't go anywhere. Eddies can stretch along the wall, but they can't stretch perpendicular to the wall, right? Okay, so this makes the turbulence very anisotropic. Okay, U prime component would be much larger than V prime or W prime, okay? So the Reynolds stress is normal to the wall, reduce in magnitude, and the turbulent production high because there are very high gradients near the wall, okay? So the wall has high gradients, high production, high shear strength, and anisotropic. So the two ways of handling turbulence near the wall. One is to modify the turbulence model so you can go all the way to the wall, right? That could be a bit of a problem, okay? Turbulence model need to be damped near the wall because you saw there was a viscous region, that means molecular viscous region very close to the wall, okay, where Y plus is less than 5, okay? So there, you don't have any turbulence energy. It's practically laminar flow, okay? So the large number of cells are required to resolve that, okay? So that's why you don't normally use that, though there are models such as Bill and others at Imperial College developed a number of variations with working with Londra. So this is basically where you have these models that go to the wall, okay? So if you do that, the first cell center should be within Y plus of 5. Okay, actually Y plus of 1 is recommended. That means you may need just 10 to 12 floods grow the structure. Okay, very resource intensive, very time consuming. So what do? What we do is we do special treatment near the wall. We say we are not going to bring K epsilon model all the way to the wall. Okay, the boundary layer structure consists of viscous sublayer from Y plus to up to 5, then a buffer layer from 5 to 30, then an inertia sublayer from 30 to 200, okay? So what we're going to do is that log law starts operating in inertia sublayer, okay? So this information is used. So what we do is we say, well, go to a place, something like a Y plus of 30, and start the K epsilon model from there. So what we do near the 30 is what makes it interesting, okay? So I don't want to go into that detail. If anybody's interested, write to me and I can point you, or you can go to the web these days and see what is done for different wall models. Imperial College was one of the first ones, Spalding was one of the first one to devise what's called the wall functions, which basically isolate the K epsilon model from the wall, and between the wall and the K epsilon model empirical data, based upon empirical data, certain functions were imposed, which gives you the starting shear stress. Okay. So the next one, if we don't want the linear eddy viscosity, which we know near the wall, there is not a isotropic viscosity. We know near the wall, eddies are stretched in one direction. It's not isotropic turbulence. So it can't be isotropic eddy either, right? So we need to go to non-linear, you might say, or anisotropic eddies, and Reynolds stress transport or some kind of models. And then there are simpler versions such as what you call algebraic stress models. All those I'm not going to discuss in detail, but let's put it this way, that when you have swirling flows, when you have certain kind of secondary flows, when you have strong curvature, strong pressure gradient, strong 3D effects, then be careful when you use the linear eddy models or K epsilon type of models or any models of that kind. They lose accuracy in such circumstances. So let's look at large eddy simulation. What does that do? It's motivated by limitations of other turbulence models, okay? The computer costs are, of course, much more, order of magnitude more, but it's much less intensive, resource intensive than DNS, which is practically impossible, except for lower Reynolds number for certain class of flows, okay? The idea is to capture the large energy containing and say the small eddies are universal, right? K epsilon says that too implicitly. Okay, when we say isotropic turbulence, we say we can use one length scale, we can say we can use one eddy viscosity. They're also assuming universality. So it's no different that way. Okay. So the large eddy we can resolve, right? Okay, we can have grid points. Then there are small eddies which are smaller than the grid scale. Okay, we can't go to the small grid scale to capture these. Okay, these are Kolmogorov eddies, we can't capture them. They can't be resolved. We don't have the resources. Okay. So that's what we're going to do. So here is how we decide what to resolve. Okay, this is the Kolmogorov energy scale, right? Okay, so we must resolve at least this part. Okay, about 80%. I mean, it's not a rule of, it's a hard, not a rule of thumb, right? It's a rule of thumb, not a hard rule, right? But you must resolve most of this. Okay, then after that, you can say, okay, I'm going to ignore these and I'm going to use the epsilon to that one. Okay, so we resolve only that part. We stop at this length scale, what this implies. Okay, so we apply a low pass filter which says average the filter equation not with rands, but average them so that small eddies are cut off. Okay, and this is filtering, not averaging. Okay, we filter them out. Okay, it does not obey the properties of averaging. You're just cutting them off. Okay, so the filter velocity is still 3D time dependent, right? It represents the motion of eddies larger than the filter width. So I could say my filter, it's like putting a sieve there and saying any eddy that goes through the sieve is not of my concern. I'm going to think of things bigger than the sieve. So when we do that, the unresolved scales are the subgrid scales. Okay, unresolved scales are the subgrid scale. They are smaller than our grid, so they're subgrid. Okay, so the typical velocity approach in this one is that the shear stress is again given by linear viscosity here. Okay, it's 2 nu t times a strain rate. Okay, so there is a strain rate directly appearing here, which is like a shear stress thing that appeared in the other one. You can relate this actually very easily because for simple flows, this strain rate will be nothing but du dy. Okay, so that's what would happen. So here we define the strain rate in this manner. Okay, Smogrinsky was one of the first one to come up with this. Okay, so his eddy viscosity model basically said that nu t is equal to a length scale delta times this shear stress. Okay, right? Okay, and And here is the shear stress, 2 nu to Sij. Here is the Sij. Okay. So this is what Sij, the strain rate here is. It's the average those strains multiplied by constant, which is typically called Smogorinsky constant. It's like set to 1. He was one of the first one to play around with this one. And the question is, what is this delta? Okay. We can take delta typically to be some function of the grid, because the smallest grid that, it's the subgrid scale we're trying to resolve. So it's related to the grid. Okay. Quite often delta is taken to be, let's say, some function, like some fraction, like 1/4 or 1/5 of the grid. Okay. So alternate to Smogorinsky model, then people start improving them. They said, well, let's use the dynamic changes in these things. Okay, they use dynamic Smogorinsky models, and then they use one equation model. So there's all these things to improve on the Smogorinskys, just like people improved on the mixing length model. Okay, so good rule of thumb is that the delta should be at least 1/5 of the length scale of certain length scale of this one. So it's less than, sorry, oh, this L is different. This is L is this distance, K 3/2 over epsilon, that distance, not the grid distance. It's smaller than the grid size or related to that somehow, like 0.1. And this is that one. So 1/5 should be the length based upon the grid size at that one. But this delta could be 5 times this one. This is one way. And this you determine from the K equation you solve, or the omega equation solve. So what happens is, typically you use a precursor RAND simulation to determine K and omega, okay, to estimate the length scale. Then you note that there'll be lower turbulent kinetic energy, which will have lower scales. Okay, so we'll need more cells for that resolution. So delta can be taken as cube root of cell volume, and then it's multiplied by constant, so becomes smaller. CS is there. So it is recommended that we take the RAND's precursor relations from K epsilon, K omega, and determine those as the initial conditions for the LES. LES, you cannot apply LES to a flow with turbulence energy is 0. Nothing would happen. So you have to have an initial field. So what is the initial field? How do we get the initial K and omega? Right? It's just like in actual life also, if laminar flow is there and there is absolutely no disturbance, like you take it out to the space and don't vary it at all, you can have flow at very large numbers, much larger numbers than 2000, which is laminar. Okay, the turbulence must be initiated by some kind of an external disturbance, whether that is in the equipment, that is in the flow, something would happen. Something stochastic has to start. That is very important to realize. So after you've done that, you do some post computation. You should carry out the assure that the turbulence kinetic energy has been resolved. You do several point probes, you do flow fields, and all things of that nature. Okay. Now let's look at the post computation checks that we do. The turbulence fluctuations can be obtained by taking the difference between the instantaneous values and the time averages. Okay. The resolved turbulence kinetic energy can be obtained as K resolved is half times the energy of the fluctuating quantities, right? So that means the subgrid scale energy can be calculated and from one equation model, and then a subgrid scale K can be directly computed. Okay, so we have resolved this. We haven't resolved the subgrid scale K, so that can be estimated from one equation model. So it can be obtained from the eddy viscosity also. Now here are some useful books and references, okay, that you may want to look at, and if you're interested in this topic. And the summary is that there is we provided you with a brief introduction. As I said, typically it should be at least 8 lectures or maybe 10 lectures to do what turbulence really is and to give you the full idea of the field. I haven't told you much about the Reynolds stresses, the algebraic stresses, the LES and all that, just given you a flavor of things so you can go and do something by yourself. Okay, so the emphasis has to be on developing a physics-related intuition, right? Turbulent flows are characterized by a wide range of length, velocity, and time scales they're highly vertical, they're highly stochastic, and they have length scales going all the way from a length scale, which will be the smallest scale, would be the Kolmogorov scale, and they go well above to the scale of the equipment or some fraction of that. These are the large eddies that carry most of the energy, okay? And the smallest eddy that dissipated. If that wasn't the case, if everything happened in large energy, large eddies or small eddies, we won't need these complex system models, okay? We know we'll have general, like if everything was isotropic, well, the mixing length model would work very well because we know the relation between them, okay? So these models, we've given you some idea, okay? We've given you some idea, large eddy models, and I've allowed plenty of time for questions because I know you'll have different questions. I know not all of you are actually interested in turbulence and understanding it per se. So I've skipped some of the advanced details for that reason, but please feel free to raise questions, to satisfy your curiosity, to ask me. If I know the answer, I'll give it to you. But I can tell you, if anybody who says that I understand turbulence, I think you want to go away from this person. Let me tell you a little story at the end. It's a story that I found very interesting. There was one of the greatest mathematicians of this century and physicist, Feynman, okay? I like him a lot. I always tell people, read his book saying, what do you care about other things? But what he did was he became famous for inventing quantum chromodynamics, okay? It was a very complex subject, and he developed a series of sketches, you might say, pictures, drawings that could well explain the quantum chromodynamics, some charts that he developed, right? He became very famous for that. It made people understand that much better, what was happening, okay? After he had done the quantum chromodynamics, he was interviewed on the PBS here. He was at Caltech, and I would go to listen to his lectures. And he, in this interview, he says, the guy asks him, the reporter asks him, Mr. Feynman, you got your Nobel Prize, you've done such a great thing. What are you going to do now with your life? You're still young. He says, looks around and thinks, and then he says, you know what I'm going to do? Turbulence has been around us for 200 years, and nobody has been able to solve it so far. It's a very tricky problem. It's the most difficult problem in physics we face today. So I'm going to give my attention to turbulence, and I hope I make some progress. Just before he was dying, unfortunately, he died of a cancer. And there was another interview with the same channel, and he was asked, okay, have you made any progress with turbulence? He says, that is my greatest regret. After 10 years of trying it, I haven't been able to make any significant progress. Well, don't be discouraged by that. There is a lot of things that you can do. Depends on your interest and depends on how much time and effort and energy you want to put in it. Thank you very, very much for your time. And here I am.